There we're going to use linear algebra, more specifically eigenvalues and eigenvectors, to derive a very efficient approach to calculating numbers in the Fibonacci sequence. So we're going to start using basic approaches, naive approaches, which you should be familiar with, or most people are familiar with. This one is a recursive approach, so that doesn't need much explanation. So we know that the nth term is equal to the sum of the two previous terms. So we use our recursion here, and we have our base cases here. Then we also have this version which uses a list, so we just append to the list and then add the last two elements of the list. Okay, so both approaches are quite slow. This one has a time complexity of 2 to the power of n. This one has a time complexity of O of n. So now we can run this little function here. This function is going to calculate the first 20 terms of the sequence and output the time taken for each one of the functions to execute, to run. So we can just run this, and we see that the first function took this long, second function took this long, which is much less than that. So we can already see that this approach is much faster. But still, O of n is going to become too slow if we increase the number of terms we want to calculate. So for example, if we did 100 here, we probably take too long. Let's try. So we put 100 here. This time it took 0.0004, which is still reasonable. Now 1,000, still going okay. 10,000. See, that's where we start to, it's not gonna finish in a reasonable amount of time. 7 seconds. It's okay, but we can do much better. So now I'm going to derive these equations here, which give us a closed form, which you're going to see that's going to give us a much more efficient approach. Okay, so let's start with a general recurrence relation. So in this relation, we're relating the nth term, the nth plus 1 term, with the nth term. So we can see here what we have here. This is our relation, a basic relation with some matrix A. So now we can say that x1 is A times x0, just using this relation here. Then we can calculate x2 and x3, and we quickly realize that xn, a general term, is a to the n xn. Here. That becomes quite obvious quite quickly. So this is we can calculate terms in the sequence using a to the n xn, but you might notice that exponentiating a matrix is very hard to do computationally. It's quite computationally expensive, and it may also be quite hard to determine a formula for the exponentiation. It might not be obvious to determine that formula. So now, a way to get around this and determine a quick formula for exponentiating a matrix or calculating a to the power of n is to use eigenvalues and eigenvectors. So just to remind you, an eigenvector is a vector that when multiplied by a matrix gives a multiple of that vector. So in this case we have ek. When we multiply ek by a, we get ek times some constant lambda k. And this constant is called the eigenvalue. The eigenvalue, lambda k, corresponds to the eigenvector ek. So now what we can do is we can write x naught, the first term in our sequence here, as a linear combination of eigenvectors of A. So here. So we need to note that this only works if the eigenvectors, if they're linear independent and they span the entire subspace. Because otherwise we might not be able to represent x naught in terms of the eigenvectors. Then calculating x1, we do the same thing, a times x naught, like here. But this time we can expand x naught in terms of the eigenvectors of A and some constant coefficients. Then using we can obviously exchange the order of the constant here. We can take the constant out front. Like you do that in every term, and we also use the distributive property of matrix multiplication by vectors to split this, take out the brackets basically, expanding them. And then we know we can also use the definition of eigenvectors here. We know from above that A times an eigenvector is going to give us an eigenvalue times the eigenvector. So then we can replace A times the eigenvectors with some constant times the eigenvalues. And then if we keep repeating this, we would see that the nth term is just a constant coefficient times the eigenvalue to the power of n times the eigenvector. So I'm going to do an extra example. Let's do x2. So we had x1 there. x2 is just a times x1. This is equal to a times c1 c1 lambda 1 e1 plus c2 lambda 2 e2 plus ck lambda k ek. So all I've done here is put this in here, replace x1 with that. Now I can do the same thing I did before and expand this out. So I can do c1 lambda 1 a e1 plus c2 lambda 2 a e2 plus ck lambda k a ek. And now I know that a e1 is just lambda 1 e1, a e2 is just lambda 2 e2. So then we know that this is equal to c1 lambda 1 e1 plus c2 lambda 2 e2. And that's right up the rest. So this is just c1 lambda 1 squared e1 plus c2 lambda 2 squared e2 dot dot dot. So we see that x2 second term we square all the eigenvectors, and then this generalizes quite nicely, and for the nth term we just raise each eigenvector, each eigenvalue to the power of n. So now we can move on to the Fibonacci sequence. So the Fibonacci sequence, is just 0, 1, 1, 2, 3, 5. So the nth term is the same as of the two previous terms. So as a recurrence relation, we have this. But this one is a second order recurrence relation, while the one at the start, this one, was a first order one. So we need to find a way to convert from a second order recurrence relation to a first order one. And we use this clever trick by inspection, really. So we create a vector with fn plus 2 and fn plus 1. That's going to be our xn plus 1. And then this is going to be a, and this is going to be x to the n. So basically this, what it shows here. This is our xn plus 1, a, x to the n. So now what we have here, by using this trick, letting xn equal fn plus 1 and fn, what we have here is a first order recurrence relation that's no difference to this. It's exactly the same thing, exactly the same situation. So now we can find the eigenvalues of A, our new matrix A. And to find the eigenvalues, we know we have to do the determinant of A minus lambda I. This gives us this. Right. And then we get this equation, a quadratic. We can solve this using the quadratic formula, completing the square, however you want. And then we get these two eigenvalues. You might notice that this is called the golden ratio, which is the ratio between the two terms, adjacent terms, as n tends to infinity. So that's a story for a different day. And then we also need to find the eigenvectors. We can do this using this. So the eigenvectors, we know that eigenvectors form the null space of A minus lambda I. So here we solve to find all the vectors in the null space, non-zero vectors in the null space. then we see that y can be any number, because this is always going to be equal to 0. So we got two equations. This is the first equation, this is the second equation. Then we get this quadratic, we factor out y and we get this, but we know that this is always equal to 0 from here. So we know that y can be any number, but in this case we're going to set y to 1, and then to get x, we just use inspection. We see that if x equals lambda up here and y is equal to 1 in this equation, we get this, and if we let x equals lambda, we get the same quadratic, and we know that works. So x equals lambda is a suitable solution by inspection. So lambda can be either of the two eigenvalues. So x can be 1 plus root 5 over 2 or 1 minus root 5 over 2. So we get our two eigenvectors here. So this eigenvector corresponds to lambda equals 1 plus root 5 over 2. This eigenvector corresponds to the eigenvalue lambda equals 1 minus root 5 over 2. Okay. So now the next step, as we showed here, is to write x naught in terms of eigenvectors. So we have our eigenvectors and our x naught as well. So then we can just set up the equation. Now we know that x naught is just the first and second term in a vector. So we know that the first term is 0 and the second term is 1. This should be f of 1, f of 0. Okay. So then we just solve the equations. We can see we use the top elements of the vectors to form this equation, and then we use the bottom elements to form this equation. Then from this equation we know this, and then we can just plug c1 equals minus c2 or c2 equals minus c1 into the first equation to get this. Then we can solve that to get c1 equals 1 over root 5 and c2 equals minus 1 over root 5. So this is just trivial algebra. The working out is not massively important, it's just the logic. So then we can get x naught or u naught, whatever you want to call the first element, has this linear combination of two eigenvectors. Okay, so then we've got everything we need. So we have x naught in terms of eigenvectors. So now to get xn, we already know the formula. It's just x naught, but then for each term we multiply by lambda 1, lambda n, the eigenvalue, raised to the power of n. So that's what we'll do here. We've got the eigenvector xn, x1, c1, x1, c1, then lambda 1 to the n, x2, c2, lambda 2 to the n. And this is equal to f of n plus 1, f of n here. So then what we're really interested in is f of n, because we want the nth term, not the n plus 1th term. That's not that useful. So then we just use the bottom elements of all the vectors of this equation here. So if we just focus on the bottom elements, this element here, this element here, this element here. So we know that this is going to get multiplied here, this is going to get multiplied here. So we're going to get f of n is equal to this. So then we get the closed form for f of n. We don't need to use for loops, we need to use recursion. We can just straight away calculate the closed form, give us n, we give you the number straight away. So this would be O of 1 if we could do square roots in O of 1 time. But the thing is, square roots are done in O of log n time. So then this solution ends up being O of log n because of the square roots. So then there's one thing we can add. So I'm not going to derive the reason why here, but this term here, the second term, in the equation is always less than 0.5. So then if we round the value, subtracting this term doesn't change what we get. So for example, if you have 2.3, if we subtract a number less than 0.5, we can be certain that we're never going to be able to change what it rounds to. Let's say 2.3 minus 0.5, that's going to give us 1.8. That still runs to 2. Either way, it runs to 2. So subtracting 0.5 is never going to change the result. So we can do this further optimization of just doing round and then dropping the second term here. That's going to be our version 4. Okay, so now we can go back to the code and implement this solution. Okay, so we're back to the code, and now here we implement the version 3. This is where you use the formula we derived, the closed formula, the full one. And this is just a bit messy, but it is the formula. We have to be careful with the brackets to ensure we do the division in the right place and the exponentiation in the right place. This is the formula. Then for version 4, as we discussed, we drop this term here. The second term can be removed and we just round. Because we're going to get a decimal. By dropping that term, it's going to give us decimal numbers. But if we round, we're going to get the correct integers because we're looking after integers. We still need to round the first one because computers don't have unlimited accuracy. So we're always going to get a number just like 0.0001 off an integer. So rounding just makes it a precise integer. So now we can test these versions. So if we start with 100 iterations, now let's start with 20. Now we can put all 4 versions side by side. So then let's add version 3. And version 4 as well. So then we're going to do the first 20 numbers using all 4 versions. Okay, so let's see the results. So version 1 took 0.0202 seconds. Version 2 took this long, as you can see. Version 3 took this long. And version 4 took this long. So this is great. We can see that, as we expect, version 4 is faster than version 3. Version 3 is faster than version 2. So our theory is working because our versions are, each one is more efficient than the previous one. So now let's start to do like 30. So now we should see a greater difference. So this one shot up to 0.16. This one is remained fairly constant. These two, this one's even gone down, the last one, version 4 has gone down. So then if you do 1,000, we know that version 1 and 2 would just crash, take too long to do. So let's just do version 3 and 4 and turn the output to false so we don't show, because otherwise it'd be a mess. Then let's see. Okay, so this one 0.010 is quite good. This one obviously takes less. So let's just for curiosity, let's try version 2, see if it actually finishes. Let's take this off, sorry. So version 2 took 0.03475. Version 3 and version 4 took way less. Let's do 10,000. Yeah, so this is where version 2 breaks down, you can't finish. Let's do 3,000 then. Yeah, result is too large. Yeah, this is just starting to break. Yeah, I think 1,000 is like the limit we can do, because otherwise the numbers get too large. But yeah, so then let's just finish off in here with this. Okay, so we can see we started with the naive approach, the recursive approach, which is very elegant in code, very intuitive to implement, but is very slow, as we saw. Then we used lists, which is I think is quite a cheat. It's not very nice, very elegant, but it's much faster than this one. Then we use these two extremely fast approaches, which is eigenvalues and eigenvectors. So applied linear algebra to solve a real world problem. It's not really real world, but we see that linear algebra has applications in computer science and can be useful for optimizing algorithms. So I can also discuss in future videos the PageRank algorithm, which can use linear algebra as well, and eigenvectors and eigenvalues. They're very useful constructs. Okay, so that's it for today. Please like and subscribe. Thank you.